Okay, so now we want to write down the matching condition for the coupling. And if you remember, for the coupling strength, the equation was the following. So for the coupling strength, um, so we started off, we said we should take the 4-point function. Now, I actually want to just discuss something before we write this equation down. There's a couple of different ways that you could formulate your description. So I just want to discuss those. Okay, so this is a little bit of an aside. When I think about a 4-point function and I think about labeling my momenta, it's perfectly acceptable to have all of the momenta incoming. Okay, so I'm going to put all of the momenta ingoing. And for example, if I wanted the conservation of energy momentum, then what that equation would read here is we would say P1 plus P2, okay, is 4 vectors, plus P3 plus P4 is equal to 0. You might also want to describe things in this way. So you might want to say, well, P1 and P2 are incoming momenta. The two particles come in, and P3 and P4 are outgoing. Okay. In that case, now the conservation of energy momentum would say P1 mu plus P2 mu is equal to P3 mu plus P4 mu. The nice thing about the first description is that we treat P1, P2, P3, and P4 as exactly the same. There's a symmetry between them. They're all incoming and nothing distinguishes any of them. In the second problem, particles 1 and 2 are incoming and particles 3 and 4 are outgoing. It's in the second problem that actually we're treating the physical momentum. We're paying attention to the physics of the problem. In fact, in the second problem, if you looked at the energies of the particles would all be positive. And this, of course, is what you expect. Energies must always be positive. In the first description, you would actually find that P3 naught is negative and P4 naught is negative. Well, if any of your energies are negative, what it's telling you is if you've drawn them as ingoing, they're actually outgoing. Okay, so either description is perfectly valid. The second description is probably more physical in the sense that you're writing down the physical momenta that your particles actually have. But the first description is often more convenient theoretically because it allows you to make manifest any symmetries that there are between all of the 4 momenta. So I just wanted to point out that there were these two different descriptions. Okay, so that was just an aside. You'll see people using both. Don't get surprised. It is basically a different notation. Okay, so I like the one with all of the momenta ingoing. So we'll stick to that. So there's P1, P2, P3, and P4. And then we said we have to take the connected piece. Good. And we said we need to amputate the external lines. So the dash means we amputate the external lines. And then what diagrams do we have? Well, the first diagram that we can have is just that diagram. That one's perfectly acceptable. Then we would have a diagram that looks like this. Okay. And let's assign the momenta. So if we call this momentum flowing up here L, and this is momentum P1, this is momentum P2, the total momentum flowing into the vertex is L plus P1 plus P2, so that has to be the momentum flowing out of the vertex. So now I've assigned the momenta for those two internal lines. There's another Feynman diagram that would look like this. And we've again got our P1, P2. Here's a loop momentum L flowing there. Actually, sorry, let me call this momentum at the bottom L. Then what do I have flowing into the vertex? L plus P1 plus P2. So what must flow out of the vertex? L plus P1 plus P2. Good. And then there's actually one more diagram I can draw. So it'll look like this. Okay, that there, there, and there. So you see in the first diagram, I have paired legs. Oh, sorry, I want this to be momentum P3. This will be plus P3. So just correct that, sorry. So for this diagram, we've got P1 and P3 flowing in. So there's L flowing in and L plus P1 plus P3 flowing out. So the first diagram is has P1 and P3 flowing in at the vertex. The second diagram has P1 and P2 flowing in at the vertex. The last diagram has P1 and P4 flowing in at the vertex. So we can either have 1 and 2 flowing in at the vertex, 1 and 3, or 1 and 4. So it's only these three possibilities. Then the momentum flowing in the second line I've denoted with a red arrow. And what's the total momentum flowing into the vertex? Well, it's L plus P1 plus P4. So what will be the total momentum flowing out? Well, it'll be L plus P1 plus P4. So what you can see is I'm doing nothing more than assigning momenta to these diagrams according to momentum conservation, and I have fixed the momenta of the external legs. Okay, so this has been quite a simple step so far. And then this is plus order G squared terms. We've added up the tree diagram plus the loop. Okay, so now let's start translating these into actual expressions. So for the first diagram sitting over there, there's a single vertex, so we'll have minus 4 factorial I G Z squared. There's no closed lines, no equivalent lines, no equivalent diagrams, no equivalent vertices. So there's no combinatoric factor to take into account. And remember, the dash tells us that we should not write down the rules for the external legs. So we should drop the external legs. So that's that's all that the first diagram is equal to. Now let's write down the second diagram. Well, there are two vertices. So we'll have minus 4 factorial I G Z squared. This is squared. Then here there is a symmetry factor, so no closed lines, no equivalent vertices, no equivalent diagrams, but there's two equivalent lines because those two lines forming the loop have the same start point. They both start at the top vertex and the same end point. They both end at the bottom vertex. So we need to divide by a factor of 2 for equivalent lines. Then we'll have an integral d4L over 2 pi to the 4, so integrate over the internal momenta. We'll have I over L squared minus M squared plus I epsilon, and I over L plus P1 plus P3 squared minus M squared plus I epsilon. And again, we don't include the external legs, so that's the complete expression for the second Feynman diagram. Now let's write down the expression for the third Feynman diagram. So again, two vertices. So we'll have minus 4 factorial I G Z squared squared. Now for the combinatoric factor, well, no closed lines, no equivalent vertices, no equivalent diagrams, but there are two equivalent lines. The top line in the loop is equivalent to the bottom line in the loop because they all start on the left vertex and end on the right vertex. So those two lines have the same start and end points. So we need to divide by 2 for equivalent lines. Then we need to integrate over the loop momentum. So this will be 2 d4L over 2 pi to the 4. And then for the first line, we've got, oh, sorry, guys, you shouldn't forget the z inverses associated to the propagators. So we'll have IZ inverse L squared minus M squared plus I epsilon, and then I Z inverse into L plus P1 plus P2 squared minus M squared plus I epsilon. Great. And now we only have one more diagram to do. We will continue in a moment.